Good morning, students. So in the last few classes, we discussed to obtain the eigenvalues and eigenfunction from the exact solution of Schrodinger equation for any Hamiltonian. And of course, we discussed some models like infinite quantum well, finite quantum well, a linear harmonic oscillator, penetration problem, hydrogen atom, and rigid rotator. In all those models, we had a Hamiltonian, and which corresponds to Schrodinger equation, and we could able to solve the Schrodinger equation for the solution, which is nothing but wave function and corresponding energy eigenvalues. So exact solutions have been obtained from Schrodinger equation of any Hamiltonian for those models. So we know already. And after that, we discussed about the perturbation theory, which we are going to apply small disturbance for the potential energy. And we are able to solve not exactly with the Schrodinger equation, and we are able to get some energy corrections. So we added those corrections with the exact solution. First order correction or second order correction, third order correction, and goes on. And in fact, we discussed two methods. One is degenerate method, another one is non-degenerate method. In non-degenerate method, we obtained the solution, which is nothing but the expectation value of the Hamiltonian, perturbing Hamiltonian. And we were able to get the energy corrections, and we added. And in the degenerate cases, we could able to diagonalize the matrix of perturbing system, and we were able to get some corrections. And a famous example for degenerate case would be the Stark effect, which we discussed in the last class. And in this case, variation method, today we are going to discuss, there will be no solution. Hamiltonian will be there, Schrodinger equation will be there, and we are not able to find any solution. So there will be no solution. So for which, how we are going to handle? For a system, for a quantum system, particular Schrodinger equation for a particular Hamiltonian, there will be no solution at all, exact solution in the earlier classes. Whereas here, there will be no solution. We are going to guess the solution. We are going to guess the wave function for this particular method. This method, variation method, is an approximation method for any bound states. And this is very, very useful method. And in fact, as far as I am concerned, this is the best method to get energy eigenvalues, wave function, which we are going to guess the wave function, energy eigenvalues for any quantum particle system. And this is the best method as far as I am concerned. Because nowadays people get a lot of acquaintance with the computers. And we know the energy eigenvalues for the corresponding system experimentally. Suppose we are going to guess the wave function, and we are going to compare with the experimental value, and whether it is exact solution or not, we are going to find out. So that's the idea about variation method. And lot of softwares are available, lot of packages are available nowadays. Lot of software in the sense like DFT, density functional theory, quantum espresso, and we have quantum espresso, and many softwares are available. Many packages are also available. Many packages in the sense we have MathCAD, MATLAB, Mathematica, and all those packages will give some solution. They all use variation method. So all the packages and all the softwares and whatever it is available in day-to-day life, and we are going to use only variation method. So variation method is the best method to find out for any quantum system, to find out the structure of the molecule, structure of the atom, and so on. And you know, the latest software is Gaussian software. That also it's available. So you know, we can get the energies for a particular quantum system. That is, energies means we are going to get the binding energies for the system. And from this binding energy, we can get a lot of electronic properties. For example, we can get optical strength, oscillator strength, transition life time, and corresponding optical properties also we can get. So from electronic properties, we can get optical properties like refractive index, changes of refractive index, absorption coefficient, second order, third order harmonic properties. So those properties we can, even Raman effect also we can get it from these electronic properties. So this is very useful method, variation method. So in the variation method, our idea is we are going to guess the wave function. So we are going to guess the wave function. In the sense, I am going to have a particular wave function. You can also have one wave function. And you can also have another wave function. So we are going to guess the wave function. And we are going to, so this wave function will contain variational parameters. Some parameters it will contain. So we are going to guess the wave function. In this method, we are going to guess the wave function. This wave function will contain some parameters. What we call this as variation parameters. We are going to minimize the Hamiltonian and thereby the energy with respect to the variation parameter. Okay, so I repeat, we have the wave function which contains the variation parameter or parameters. Okay, we can have many more parameters, doesn't matter. More parameters, the more accurate answer that we are going to get in. Okay, for example, you are going to apply perturbation, magnetic field, you are going to apply electric field. Already we have one variation parameter. So the moment we are going to apply the magnetic field, we can add one more variation parameter. Electric field, we can add one more parameter. So the more variation parameters, the more accurate answer that we are going to get in. So number of variation parameters matter. So now the thing is, we are going to vary the variation parameter. We are going to minimize the Hamiltonian and thereby the energy with respect to the variation parameter and get the energies. Okay, this energy will be always greater than that of the actual energy. Will be always greater than that of the actual energy. Actual energy means it's a true energy for the system. Okay, for example, if we have a hydrogen atom, the binding energy of the electron in the proton in hydrogen atom is given by, we have already studied, it is minus 13.6 electron volt. Okay, we know already this. Suppose you are going to choose one wave function and you are able to get the energy eigenvalue minus 12.5 electron volt. Okay, minus 12.5 electron volt. I am going to choose the wave function, another wave function, and I have obtained, for example, I have obtained the energy eigenvalue which is minus 12.8 electron volt. Okay, so your energy will be minus 12.5 electron volt, my energy would be minus 12.8 electron volt. What are the actual energy by experiment? It is minus 13.6 electron volt, which is very closer. The wave function which I have chosen is closer to the actual energy. So this is a way that we are going to guess the wave function. Okay, we have to guess. Guess in the sense it depends on the system. Suppose we use the particle in the quantum well box, particle in a box. We are going to use the particle in a wire, quantum well wire. We are going to use the particle inside the dot. So it depends on the system first. And second one is, the guessed wave function should have some admissible, physically acceptable properties. Some properties. What are the properties? We have already studied in the earlier classes. Some properties. For example, the wave function should die out at the end. The wave function should die out at infinity. So we know already this property. Okay. And there should be no nodes. For any wave function, there should be no nodes. Suppose if there are nodes, the wave function will have zero amplitude. If there are nodes, the wave function will have zero amplitude. If there is zero amplitude, there will be no probability of finding the particle in the system. Almost correct. So there will be no wave function. So there should be no nodes. And of course it should be continuous, it should be smooth, and differentiation also should be continuous. So we know those properties. According to those properties, we will have to choose the wave function. That is very important. Then another very important thing is variation method is the best method which is applicable for hydrogenic system, hydrogen-like system. And of course people will use for helium system also. Hydrogenic system or hydrogen-like system in which we have a single electron and a single proton. So this is applicable for this quantum system. So we know already. And suppose if we have any complex system, for example silicon doped with phosphor, we will consider silicon doped with phosphor. Silicon has 14 electrons. Okay, silicon has. And of course we have K element shell. The first shell will contain 2 electrons. The second shell will contain 8 electrons. So 2 plus 8, 10. So out of 14, we have 4 electrons are left out. Okay, 4 electrons are wandering. Suppose I am going to dope silicon doped with phosphor. I am going to dope silicon with phosphor. Phosphor contains 15 electrons. Okay, so 2, 8, 5. 2 in the K shell. Then next shell will have 8, so 5. Now I am going to dope these two elements. So 4 electrons from silicon, 5 electrons from phosphor, they will have covalently bonded. Okay, and they will fulfill 8 electrons in the shell. Remaining 1 electron is left out. Correct? 4 plus 5, 9. So we need to have the orbit 8 electrons. So remaining 1 electron is left out. Correct? This single electron exactly acts as a hydrogenic system, like a hydrogen atom. In the hydrogen atom we have a single electron. So similarly this system also can be considered as a hydrogenic system or hydrogen-like system. Okay, so this can be useful now. This can be useful. So variation method can be applied for silicon doped with phosphor. Actually speaking, this is a complex system. It is not hydrogen atom, but hydrogen-like system. So this can be used. So silicon doped with phosphor. This is for the single element. Silicon is a single element and phosphor also single element. We are going to dope with silicon, so what we call the single element. Whereas we can have 2 alloys, 2 elements joined together, gallium arsenide. It's a binary material. That can also be used. Okay, variation method that can be used for binary material, gallium arsenide. For ternary material, 3 alloys joined together, 3 elements joined together. For example, cadmium, zinc, telluride, CD, Zn, Te. So 3 materials that also can be used if we consider as a hydrogenic system. 4 materials, quaternary materials, 5 materials, quinary materials. So nowadays people use this variation method for 5 materials joined together, quinary materials. So it's very useful method. And of course we can find out the solution. We are going to guess the wave function and we are going to find out whichever the guessed wave function which is very closer to the actual energy. So we are going to guess. So this is the way that the variation method is. Okay. So with this the introduction, the sketchy preamble, and we are going to look in the variation method in detail. So in this class we are going to discuss these two. Okay. In the next class we are going to have the applications of variation method. Okay. So variation method, we are going to have the proof and demonstration, and variation method for the excited states. And of course, as I said, variation method is the best method for any hydrogen system for the ground state wave function, not for the all excited states. Of course, it is applicable for first excited state, it's okay. Whereas for the second excited state, third excited state, there will be lot of errors. So people will never use. So as I said, this is the base for any computer simulation techniques nowadays. All the softwares like Gaussian software, quantum espresso software, DFT, density function theory, all they use this variation method as a base. Even packages, MathCAD, MATLAB, Mathematica. So all these packages also will use this variation type. So if you are going to do any research work in quantum theory, you will have to start only with variation method. Okay, for theoretical work. So you have to start only with the theoretical variation method. So we are going to see in detail. So there exist some systems whose Hamiltonians are known, but they cannot be solved exactly or approximately by perturbation theory. So there will be no solution, exact solution, and it cannot be solved also by perturbation theory, because the first order is not sufficiently accurate, and we will not be knowing the knowledge of wave function. So we cannot have some solution for the particular Schrodinger equation for any Hamiltonian. Then one of the approximation methods is suitable for solving such problems, the variation method. So variation method, sometimes it is called as Rayleigh-Ritz method. So in the question paper, sometimes you will be asked, explain Rayleigh-Ritz method. Okay, so both are the same. To solve for approximate ground state energy using Schrodinger equation in which the solution for the wave function is not there. Okay, the first point, you are going to guess the trial wave function. For any quantum system, you are going to guess the trial wave function taking into account the physical properties of the wave function, okay, which we mentioned earlier. Some parameters will be there, variation parameters. Okay, those parameters called variation parameters. So you are going to vary the variation parameters. You are going to adjust the variation parameters, and you are going to minimize the Hamiltonian and thereby minimizing the energy for the chosen trial wave function. So which you have chosen. Okay. The resulting trial wave function and corresponding energy are the variation method approximation to the exact wave function. You are going to compare with the exact wave function and the energy. Okay, we are going to compare with the exact energy. The variation method is used for determining upper bound values. As I said earlier, that for any hydrogen atom, the binding energy of the electron with the proton in the hydrogen atom is minus 13.6 electron volt. Just now we said. And we have some values also, minus 12.8 electron volt, minus 12.5 electron volt. Those values are called upper bound values. Okay, those values. We have chosen some wave function and we are able to get some energies. These energies are nothing but upper bound values. These energies will be always greater than that of the actual energy. It will be greater because electron will tend to be in a minimum position. So in the actual system, electron, some energy values will be there. These energies will have a minimum energy always. The electron will tend to be in a minimum position to have minimum energy. All those values which we have calculated from chosen values will be always greater than or equal to that of the actual energy values. Okay, those values are called upper bound values for the eigenenergies of a system whose Hamiltonian is known, whereas its eigensets will not be known. It is particularly used for determining the ground state, as I said. For the excited state, it is very difficult. For the first excited state, it's okay. For the second and third, there will be a lot of error. So people never use. In the context of the variation method, one does not attempt to solve the eigenvalue problem. So we are not going to. So this is the eigenvalue equation, H psi equal to A psi. Okay, so we know already this equation 4.83. So the wave function which we have chosen, which contains a variation parameter. So alpha is nothing but variation parameter. So psi, which depends on the parameter psi alpha, which is equal to A e power minus alpha r. Alpha stands for variation parameter. As I said, you need not give one variation parameter, we can give number of variation parameters we can give. More variation parameters, the more accurate answer that we are going to get in. Okay, it's a very important thing. This variation parameter will be always inverse of Bohr radius. Okay, that is the idea. So inverse of Bohr radius. Okay, suppose I have chosen some silicon doped with phosphor or gallium arsenide. So I will have to choose the alpha inverse of Bohr radius of gallium arsenide, which is nothing but 103 angstrom. For gallium arsenide, the Bohr radius is 103 angstrom. So I have to choose in such a way that it will be nearby 1 or 3 angstrom. Okay, so inverse of Bohr radius, A e power minus alpha. Now, as I said, we are going to minimize the Hamiltonian and thereby energy. So you are going to minimize the energy with respect to alpha, because electron will tend to be in a minimum position. That's why we are minimizing, and we are going to equate to 0 and get the value for alpha. When you equate to 0, get the value for alpha. Then you substitute in the expectation value the Hamiltonian and get the value. This value will be always greater than that of 2 system value. So this is the idea. Okay, we are going to substitute it in this expression. So psi alpha depends on the variation parameter alpha in the wave function, will also depend on energy. Of course, A depends, because psi depends on alpha, E also depends on alpha. It's very clear. So the variational ansatz, this means variational wave function. Okay, ansatz enables us to vary alpha so as to minimize the energy. The minimum value of energy provides an upper limit approximation for the true energy of the system. So we have the true energy of the system, we have the value, and we have already calculated those values minimizing the energy, and those values will be always greater than or equal to the true energy of the system, which is the actual energy from the experimental value. The variation method is particularly useful in determining the ground state energy, we have already seen, and its eigenstate without explicitly solving the Schrodinger equation. So we are not going to solve any Schrodinger equation. For any arbitrary tail wave function, get psi alpha, alpha stands for variation parameter, we choose. The energy as given by 4.85, which we have said, which is always larger than that of the actual energy. So this is 4.85. This equation should be greater than or equal to E naught. E naught is nothing but actual energy, true energy from the experimental side. Okay, so here it is mentioned as greater than or equal to. Okay, so just now we have seen those values, the chosen wave functions, those values, those energy values will be greater, we said, or equal to it is given. Suppose we are going to choose the wave function in such a way that this wave function, the chosen wave function, and the actual wave function are the same, then we will get the energies will be equal. Okay, the energies will be equal. If the wave functions for the chosen one and the actual energy, if they are same, then both the energies will be equal, or otherwise it will be greater. So this theorem is called variational theorem. It's a variational principle, variation method. Okay, the expectation value of the energy calculated using tail wave function will always be greater than that of true value. This is true value or eigenvalue E naught. True value system from the experimental side. The equality condition occurs only when psi alpha is proportional to the true ground state. This is what I said. Okay. Now we are going to prove this one. To prove this, we simply expand the tail wave function. Just to expand the tail wave function, psi of alpha. So expansion theorem, we know that this can be wave function can be expanded like this. Okay. So we know already this earlier, expanded. And A naught is the expansion coefficient, and phi n goes like this. Phi 1, phi 2, phi 0 goes like this. So this can be expanded like this. A naught phi 0 plus A1 phi 1 plus A2 phi 2 goes on. Okay. Now just take the numerator of 4.86. So this is your 4.86. Just take the numerator. So you have the numerator. We are going to calculate the expectation value of the Hamiltonian. Okay, expectation value of the Hamiltonian. So this is in Ket-Bra notation. This is in ordinary wave equations. Okay, wave mechanics, matrix mechanics. That's all. So psi star h psi d tau. So we are going to get the value. Now psi is given by this one. So psi star must be the complex conjugate of this. So which is nothing but A naught phi naught plus A1 phi 1 dot dot dot, which is complex conjugate. So h, the same h is here, and you are going to write psi. Psi is given by this expression. So h is sandwiched between your ordinary wave function and its complex conjugate. Okay. Now we know that h operates on phi naught will give us E naught phi naught, eigenvalue equation, and similarly h operates on phi 1 will give us E1 phi 1. Similarly goes on. Is it okay? Fine. Now I can pull E0 is a constant, E1 is a constant, E2 is A1 also constant, I can pull it out. So we can pull it out. So just to pull it out, you have to multiply these two and we can pull it out. For example, I am going to multiply and pull it out. Okay, let us see how we are going to multiply. So this multiplied by this multiplied by this multiplied by this. First one. Second one, this multiplied by this multiplied by this, and this multiplied by this term. Suppose we are going to multiply these two, and you have integration of phi naught star phi naught d tau. You can pull a naught star and a naught out. So answer will be phi naught star phi 0. So that will be your first one, d tau. What is this one? This one multiplied by this one. You will have phi naught star with phi 1, and they will be canonical delta function. N is not equal, so this must be equal to 0. Okay, what are multiplying these two? Again 0. Multiplying these two will become 1. Okay, of course there exists a value. So we can have a naught star, a naught, e naught, first term. Okay, then a naught star, a1, e1, second term, and goes on. Is it okay? And this must be normalized, and the next one will be orthogonal. So normalized orthogonal goes on. Is it okay? So you are going to multiply these two, will have normalized. If you are going to multiply these two, orthogonal. If you are going to multiply these two, orthogonal. If you are going to multiply these two, normalized. So it goes on. Orthogonal, normalized, non-orthogonal goes on. So now the numerator equation is given by a naught star, a naught, e naught. This will become 1 plus a1 star, a1, e1. So we have calculated the numerator values. Now we will go for denominator. Denominator is given by normalization. Okay. So denominator is given by this expression. And you have psi star is given by this expression. Psi is given by this expression. You are going to multiply like this as we have done earlier. So you have a naught star, a naught, phi naught star, phi naught d tau, the first one. This will be your second one, correct? So you have a1 star, a1, okay, phi 1 star, phi 1. Other terminal will become 0. Okay, orthogonal property. So this term can be written as a naught star a plus a1 star a1 goes on. So we have obtained the expression for numerator and denominator. Okay, then we can substitute. So this is for the expression for the numerator which you have obtained, and this is for the expression for the denominator for this expression. So we have obtained. Is it okay? Any doubt? I am going to subtract E naught on both sides. I am going to subtract E naught by on both sides. So minus E naught, this minus E naught. Take the LCM. You are going to take the LCM. So multiply this one will give you this expression. Very simple one. Okay. Now you are going to subtract this term. So you have a naught star. So we have a naught star, a naught, e naught. We have a naught star, a naught, e naught. Both the term will get cancelled. Correct? First term of this and first term of this will get cancelled. The second term is exactly written like this. Okay, second term. This is your second term. And this will be second term is written here and third term is written here. Any doubt? The first term in this expression and first term in this expression will get cancelled. Now combining these two. So a1 star, a1 equals multiplied by e1 minus e0 plus a2 star, a2, e2 minus e0. Is it okay? And goes on. The denominator as it is exactly like this. Okay, very simple technique. Now look over here. A1 star A1 will give us mod A1 square, E1 minus E0 plus mod A2 square, E2 minus E0 goes on. You just right hand side, you consider right hand side. This is a positive quantity. Okay, E1 minus E0 also a positive quantity. E1 minus E0 also will be a positive quantity, and right hand side will be a positive quantity. Okay, so this value will be always positive quantity. So it's greater. So this must be a greater than or equal to 0. It is greater value. Right hand side will be greater value. So this value should be always greater, or it can be equal. Okay, it can be greater or equal. So that's why we said that the chosen wave functions which we have chosen, corresponding energy eigenvalues will be always greater than that of the true system, or it can be equal also, provided the wave function of both the systems should be equal. Only then this can be equate, that condition can be satisfied. So this is the expression we have given. This is for the particular system. For n number of system, we can have an squared is positive. So en is greater than or equal to e naught always for all the values of n. Therefore, right hand side is positive or 0. Thus we have proved that this always an upper limit energy will be your E with respect to alpha. So this will be greater than or equal to E naught. This is for the energy for the true system. This is for the energies that we have obtained from the guessed wave function. Okay? Is it okay? This condition, if condition is satisfied, using variation parameter and the wave function for the actual system, if this condition is satisfied, then we can say that this will be equal to this. So E depends on alpha is equal to the energy of the true system. If two appropriate wave functions are used, then the wave function which gives E with respect to alpha variation parameter value closer to the actual energy value E naught, which is better than the one. So usually will be better than, the better result will be whichever is the closer wave function to the true system. Okay, so this is for the n system. Okay, n number of systems. So the same condition we have written summation. So instead of integration, we have written summation over n for an square en divided by normalization constant. So this must be greater than or equal to your E naught. So this is for the non-degenerate one-dimensional bound states. Okay. So this is approximation method for the bound states. Any doubt? This theorem is the basis for the variation method for the calculation of approximate energy eigenvalue for the system. If we choose a number of wave functions psi1, psi2, psi3 and calculate E1, E2, E3 corresponding to them, then each of these values E will be greater than that of the actual energy, and the lowest one is the nearest to E naught. Okay, so whatever we have studied, we can have some following steps. Okay, based on physical intuition, make an educated guess of a trail wave function. So we have to guess the trail wave function first. Guess the trail wave function in the sense it has to obey some physical properties, physically acceptable, admissible properties of the ground state. What are the properties? As I said, no nodes, and it must be symmetry, it must be smooth, it have a continuous value, differentiation also should be continuous, and infinity it has to die out. Okay, all those properties it has to satisfy. If the properties are not sure, then we may include the adjustable parameters. We will have to use alpha 1, alpha 2, alpha 3, number of variation parameters we can use. So this is the idea. So using 4.86, we will have to minimize the energy. So here the energy is obtained by taking the expectation value. Okay, so this is for number of variation parameters. Okay, sandwiched between ordinary wave function and complex conjugate divided by normalized condition. Okay, in most of the cases, psi naught, which depends on many variation parameters, will be assumed to be normalized. Hence, the denominator is equal to 1. Always this will be equal to 1. Then what is the next one? We are going to minimize the Hamiltonian and thereby the energy. So we are going to minimize the energy with respect to alpha. So here alpha 1, alpha 2, alpha 3 goes on. Okay, suppose we are going to include more variation parameters, we have to include alpha 1, alpha 2, alpha 3. The more accurate answer that we are going to get in. So if you include more adjustable parameters, variation parameters, okay, then we are going to minimize E naught and we are going to substitute those values in the Hamiltonian. This Hamiltonian, we will get the energy. Thus the values of energy will be this one. Okay, using this equation. So the variation procedure becomes complicated as we deal with the higher excited state. So as I said, for the higher excited state, first order it's okay. For the second order, third order, the answer that we are going to get will be, we have more error towards the actual energy. As a result, this method is mainly used to determine the ground state energy, and this can be also used for the collision problem. The variation method is used to determine the ground state energy of the system, and it can be applied for the collision problem. This method uses the stationary perturbation theory. Of course, we have used only time independent perturbation theory. So we have used. It comes under time independent perturbation theory. Okay.